Hi everybody, welcome back. Right now we're going to be continuing the Breakout programming project using JavaFX. In the last video, we ended up with creating our basic game objects. We have a paddle, which can move to the left and to the right with the arrow keys. We have the basic game objects. We have a ball, we have some bricks, we have some purple walls and a nice outer space background. And now we'd like to get things moving and bouncing around. In particular, what I'd like to do today, let's see, for Breakout, part 2, some of the things I'd like to do is, well, get the ball moving. In particular, I'd like to have it bounce off the bricks and walls. I'd also like to have the ball bounce off the paddle. And it turns out the way the ball bounces off the paddle is using a slightly different algorithm, which we'll see in a little bit. I'd also like to see bricks destroyed once we bounce off of them, and some kind of score or points added when you destroy a brick. I'd like to add a reserve ball mechanic. If this is the feature when the ball is destroyed, a new ball will spawn. And finally, I'd like to give the player a chance to maybe press some kind of a key to launch the ball. When the game starts, the ball shouldn't start flying off the paddle right away. So maybe a press space to start, ball moving. And so these are the features I'd like to add today. In no particular order, we'll probably just get the ball moving first. Maybe we'll do the press space to start second, actually. All right, so that is the plan for today. All right, to begin, let's go ahead and just get that ball moving. Right, so I'm going to start off in the ball class. And last time when we worked on this class, we didn't do much other than set an animator. We just have a single image which represents this object. I'm going to uncomment the line where we set a boundary polygon. And let's set up some physics. So let's say this dot set physics to be a new physics object. No acceleration, maybe a maximum speed of 400. Now later on we might speed that up a bit. But for now, maximum speed of 400 is fine. Once physics is activated, then I can go into the physics object and set some values. I can set the speed. Let's set that to 400. And once we have a non-zero speed, we can set the motion angle. I'd like the ball to move straight up at the beginning of the game. All right, and let's go ahead and give this a run. The ball should just fly straight up on the screen when we launch the game. So let's right-click, run the main. Sure enough, there goes the ball. We can already see that it's going to be a little bit frustrating if the ball launches right away. Right, so when the ball is spawned, perhaps we should not set the speed right away. Right, perhaps when we launch the ball, so in the ball class, I'll comment this code out for now. I'd like to kind of pin the ball to the paddle, right? As the paddle moves left and right, maybe get that ball to move along in conjunction with it. But as a first step, before we even get to that, I'd like to say maybe press space to start, little message to display on the screen. If the user presses space, then the ball is activated. Okay, so let's see. I'm going to add a new object to have that text display on the screen. Let's see, a new class. I'll call this start message. This is just another actor. So I'm going to copy the template actor code into this new class, start message. Immediately, I need to change this to the class name, start message. Start message. And if I take a look in the folder for this project, in the images directory, you'll see I actually have something called startmessage.png. Right, so I wanted to say press space to start on the screen. So we'll set up the animator for this object to be start-message.png. Okay. And let's go to the level screen class. There's only going to be one of these, so perhaps I'll create a new start message called start message. I'll initialize it on top of everything else, preferably. And so after I declare all the bricks and the paddle, let's say start message is a new start message. At first, looks like I'm going to stick it in the corner. Then I'll use the center at actor method to center it on the background. Remember, I declared an outer space background. And so I'd like to center it there. So I'm going to need a reference to this background object, actually. So let's say background equals new background. And then scrolling back down, I'll say start message dot center at actor, and we're going to center it at the background. Right, so let's see if that start message appears. I always like to test the game as frequently as possible. Compiling our code, run the main method. Sure enough, it says press space to start right in the middle. Might actually end up moving that down a bit. And it could be a little bit hard to read, being overlapped by those bricks. So I might do kind of a move by and move it down a little bit. But I'll do that a little later. That's more of an aesthetic thing. So now it's indicated that I should press space to start. So let's go back to the level screen class, and in the update method, well, let's add something for pressing space. And so the code's going to look very similar to this. And so is key pressed? This is kind of a discrete event, so is key just pressed? Keys dot space. And let's say that I'm not going to move the paddle in this case. I want to say for every base actor called ball, from the base actor class, I'll run the static method getList. I'd like to get everything on the main stage derived from the ball class. And if the ball, well, what I could say is ball dot set speed 400, ball dot physics, excuse me, and ball dot physics dot set motion angle 90. That'll have it travel straight up. However, later on, one of my favorite power-ups in all of Breakout is the multi-ball power-up. And I don't necessarily want pressing the spacebar key to send all balls that might already be on the screen and moving straight up. So I'm going to add an if statement here. Only if the ball's not currently moving should we apply these two lines of code. So let's say if ball.physics.getSpeed is equal to 0. I'm always nervous saying if a double is equal to something else. Let's say if it's less than 0.001. Effectively 0, but avoiding the possibility of a rounding error. In that case, all balls which aren't moving will start them moving straight up in the air. All right, that sounds pretty good. Let's go ahead and compile and give this a run. All right, so at the beginning of the game, we have the ball there. If I press space, it goes up. Excellent. Also, when we press the spacebar key, we can probably hide the press start message. Start message dot set visible to false. We can go ahead and hide that message. The other thing I'd really like to do, I'd like to be able to shoot the ball up, but I'd also like to be able to carry the ball to the left and to the right when it's not moving. So let's also add in a bit of code. Let's also comment as we go along too. It's very important practice. So press space to start the ball moving. Let's also add in a little bit of code. It says if ball is not moving, then position it on center top of the paddle. So let's say, again, we're going to go through all the balls. We're going to figure out which ones are not moving and position it on top of the paddle. So I can actually copy some of this code here. Right, so get a list of all the ball objects and those which aren't moving, those whose speeds are close enough to 0. Then we want to set its position to be right above the center of the paddle. Let's say ball.setPosition to be, let's see, I want the paddle get its X position, then the paddle's Y position plus some amount. I'm going to guess about 48 pixels. Okay, I think this will do it. Let's compile and give this a run. All right, the ball is traveling with a paddle. I do need to move the ball down a little bit, and I also need to center it on the paddle. So we can do all of those things. That's not too bad. And so let's do it in 2 steps. Let's use our center it actor method. Let's center it on the paddle. And then there's a method, let's see, I'm pretty sure it's called move by. Yep, we can move by some amount in the Y direction. I'd like to move it up just a little bit. Maybe like 28 pixels would be enough. Let's give this a second try. Hopefully it'll be above the center of the paddle now. Not floating above the paddle, not to the left of the paddle. All right, I'm going to call that a victory. And then, oh, that's kind of weird. If I hold down the left arrow key when I'm close to the wall, it's trying to move farther to the left. We'll fix that later. For now, if I press space, now launches, it goes right through the wall. Excellent. We're going to fix that next. Okay, it's time to start talking about bouncing off of objects. The mathematics for bouncing isn't too bad, just a couple of equations. So we have a picture here to kind of talk about what's happening. So imagine you have some kind of a flat surface. Here I've got this black rectangle, and I have this ball here, which is traveling along and is going to strike the surface. We want to calculate that rebound angle, keeping in mind that all angles are measured with respect to the x-axis. One thing we know about bouncing off of a flat surface is that the angle at which you hit the surface should match the angle at which you bounce off of the surface. So what do we need to calculate here? Well, we need to calculate this angle A, first of all. And conveniently, if I were to draw this line indicating the path of the ball and continue it up through the surface. It doesn't really pass through the surface. But the angle at which the ball is traveling, I've indicated with the letter B here. And the angle the surface makes to the x-axis, I've indicated with the letter S. I'm really interested in the angle between the surface and the ball. And it turns out that I have what we call in geometry vertical angles here. This angle at which the ball hits the surface is the same as this angle I'm indicating up here. And to calculate that, I'm going to take the ball's angle of motion and subtract the surface angle, the angle at which the surface is tilted. That gives me that angle A. And now to calculate the rebound angle, I'm going to take again, the angle at which the surface is inclined, and just subtract this angle, and I'll be left with a rebound angle. And so just have two subtraction equations here. Just as a numerical example, we could imagine that the surface is tilted at a 45-degree angle, and the ball's traveling at a 60-degree angle. Right, that means the angle between these two objects is 15 degrees. Right, so there should be a 15-degree angle between the surface and the rebound angle. So to figure out the rebound angle, I take the surface, which in this example is 15. So, sorry, the surface is tilted an angle of 45 degrees. Subtract the angle of 15, and that gives me a rebound angle of 30. And the other thing I'd like to keep in mind, and this might come up a little bit later, is that the angle at which this is inclined, I could write that as 45 degrees. I could also write it as 45 plus 180 degrees. Right? Saying that this is tilted at an angle of 225 is also equally valid. And it turns out in the equations, you'll still get the same result if instead of an angle of 45 degrees for the surface, I used an angle of 225. That would give me a rebound angle of 390 degrees. But since 360 equals a full revolution, 390 minus 360 gives us the equivalent angle of 30. And so we don't have to worry too much about which angle we give for the surface. Okay, that being said, in the physics class, there is a method which calculates the angle at which you're bouncing off of a surface angle. Again, we calculate the difference between the angle of motion and the angle of the surface, and then we subtract that from the angle of the surface to get our final bounce angle, or what I called a rebound angle in the picture before. And so whenever we collide with something, we're going to bounce against it using this method in the physics class to change its angle of motion. Okay, let's head over to level screen. All right, so now this was all taking place before. This was all in the update method. No, sorry, this was on the initialization method. Now we need to move to the update method, and we want to do the check to make sure that the ball is going to bounce off of both the walls and the bricks. So let's say for each base actor, I can't spell, base actor wall, base actor.getList, everything from the main stage derived from the wall class. I would like to check to see if the ball overlaps the wall. Right, so if ball overlaps wall, in that case, I would like to prevent the overlap. Oh, I haven't declared what ball is yet. This is going to require a nested for loop in case we have many balls colliding against many walls. So let's also say for each base actor called ball, In the base actor class, get a list of everything on the main stage derived from the ball class. And if the ball overlaps the wall, then we want to prevent the overlap, but I would also like to get the data from preventing that overlap. So you might recall that we have a prevent overlap method. And this is actually in the base actor class. Let's check this out. So we have prevent overlap, and it runs some methods, and it returns what's called a normal vector. And the normal vector it describes how two things overlap. And so I'm going to store this as I think I need a minimum translation vector. And this is going to be after we prevent the overlap with a wall. It looks like I'm going to need to import a class here. I'm going to sneak a peek here, minimum translation vector. Right, let's add that import statement up top. Okay. So we've got a vector. So we're preventing the overlap here. Hang on, vector 2. Oh, this just returns a vector 2. Oh, that's even easier. Vector 2. Oh, do I need to import? Now I need to import the class vector 2. Import com.badlogic.gdx.math.vector2. Oh, much better. All right, so this was the vector by which the ball was moved to prevent overlap with a wall. Right, and so if this is not null, then we're going to go ahead and force it to bounce off of the wall. So let's say I need to figure out the angle at which the wall is, let's see, the angle at which the ball bounces off of the wall. Before I do that, I need to find the angle of the surface. And so I'm just going to draw a little diagram really quickly right here. See, if we have a surface, right, like a brick, the surface angle is going to depend on which part of the brick the ball hits, right, or which part the ball overlaps. So for instance, if the overlap is like this, right, if here's the ball, in this case, the minimum translation vector points down, right? We correct for the overlap by moving the ball down, in which case the surface angle, maybe a purple color, surface angle should be pointing off to the side here. So let's see, I'm going to get the angle of this vector, and then I'm going to add 90 degrees to it, add or subtract 90 degrees, either one of these will work, to calculate this bounce angle. All right, sometimes a little picture always helps. Okay, so first find that angle, and that'll be the surface angle. So let's say double surface angle is equal to the displacement vector, the minimum translation vector, dot, like to get the angle, and then add 90 to it. And then that ball, I would like to say the physics object has that method for bouncing against a particular surface angle. Let's see. Oh, and this should be a float. So let me make this a float. Okay, let's give this a try. Right now, we've only worried about balls colliding with walls. Let's see if the ball bounces off of the wall. I can press space to start. Hey, there it goes. And it goes right through the paddle. Fantastic. Which means we should probably talk about bouncing off the paddle next. In the game of Breakout, one interesting thing is when a ball bounces off the paddle, it uses slightly different logic in order to give the player a feeling of control. So if the ball hits the exact top of the paddle, or sorry, the exact center top of the paddle, it'll usually bounce straight up. But if you hit the left side of the paddle, the ball will typically bounce off to the left, no matter what angle it was coming in at. Similarly, if the ball comes in on the right side of the paddle, it'll bounce off to the right, again, regardless of which angle the ball was traveling when it hit the paddle. And so if the ball traveled in from the right, hit on the right, it would still kind of bounce back off. It's almost like the paddle is really shaped like a dome more than a rectangle. And so what we'd like to do is calculate the bounce angle in a completely different way for this game, something very specific and unique to Breakout. All right, so let's go to the level screen class, and we're going to actually calculate some things, but it'll be nicer if we actually write new methods for them. It'll be a little bit easier to read and understand. So I'm going to go actually down to the bottom of the class. We're going to write two helper methods. Right, helper methods for calculating, I mean, they can use in other situations, but for calculating the bounce angle for the ball off of the paddle. The first of these angles I'm going to call lerp, which is short for linear interpolation. So let's say public float lerp. And the idea is you're given kind of a low value and a high value. Let's say a min value and a max value, and then some kind of a percent. And so you want to calculate and return the value between min and max, percentage of the way across. So for example, let's say min was equal to the number 2, max was equal to the number 10, percent, let's say percent is equal to 0.5, then that means that halfway, or 50% between 2 and 10 would be 6. Right, so the linear interpolation in that case is 6. But with a different value of percent, like let's say percent is equal to 0.25. I think of that as 25% rather than 50%. Right, in this case, what would the linear interpolation be? That means we're only going a quarter of the distance between the points 2 and 10. The lerp in this case would be equal to, see, that would be 4. Right, the formula that we're interested in the value that we want to return is starting from the min value, we're going to add a percentage of the distance between the max and the min value, which is max minus min. So that's called linear interpolation. So for example, in our paddle, I've got another picture over here. And so the angle on the left, maybe this would represent, what number would that be? See, 90 degrees is straight up, 180 is to the left. Maybe this is something like 135 degrees over here. And over here, this is a 45-degree angle. Right, so we might want to choose a number between 135 and 45, depending on which one of these points the ball hits on the paddle. Right, so we can use lerp for that. The other function, which is going to be very helpful, is to calculate kind of what this percentage is going to be based on two different values. So I'm going to create a method to actually calculate the percent. Again, between a min and a max value, and I'll say maybe x. Again, let's head back over to that picture. Right, so maybe, for example, this x coordinate corresponds to, right, depending on where the paddle is located, maybe the current left side of the paddle is at 50, and the paddle has a width of 120. So this value on the right is x equals 170. And then at the moment of collision, right, perhaps we take a look at the x coordinate of the center of the ball. Right, maybe this x coordinate is something like 70. We have to determine what percentage of the way across the paddle has the ball hit. And then we take that percentage and we'll feed it into the lerp function later. And so how do we calculate the percent here? Well, what we'll do is we'll calculate, we have the difference between the max and min values. And so think of this as the min x value and think of this as the max x value. Right, we'll calculate the complete range. Then we'll calculate how far away we've gone across that range. Right, so we're going to do two subtractions and then calculate the percentage. And that turns out to be a fraction. So again, we're going to calculate how far across x is from the min. So the value we're returning here, I'm going to say x minus the min value divided by max minus the min value. So for example, if x was equal to min, we would return 0, or 0% of the way across. If x is equal to the maximum value, and this fraction becomes 1, or 100% of the way across. And then it, again, kind of interpolates for all the values of x in between max and min. All right, so we're going to use these two functions whenever the ball collides with a paddle. So let's do this. We're back up in the update method now. Again, for each ball, we're going to determine if it collides with a paddle. So here we're going to check for ball paddle collision. For each base, for each base actor called ball, base actor get list, everything from the main stage derived from the ball class. I'd like to say if the ball overlaps the paddle, ball dot overlaps paddle. Then I'd like to say, first, prevent the overlap. Ball dot prevent overlap with a paddle. This will move it off. And then I need to start calculating these different values. So let's say float the min value, which is the left-hand side of the paddle. This will be paddle.getX. Float max, that's going to be the paddle's x plus the paddle's width. Then I can calculate the center of the ball. It's important to not use the left coordinate of the ball, but the center of the ball. So let's say float x is equal to ball.getX plus the center is going to be half the width. So ball.getWidth divided by 2. And then I want to figure out the percent. Again, we'll do that from the percent function. This is how far across, what percentage of the way between min and max is x. So min, max, x. And then the bounce angle I'd like to calculate. The bounce angle off of the paddle. I'll get that with linear interpolation. And again, I think on the picture we had before, we could do something like 135 if it hits the left edge of the paddle, then 45 if it hits the right edge of the paddle. So I want to lerp between 135 and 45, given whatever that percent value is. Now that I've calculated the bounce angle, we're going to use that as the new motion angle for the ball. So ball.setMotionAngle, ball.physics. This has to do with the physics of the ball. Set motion angle to be whatever that bounce angle is. All right, excellent. Let's go ahead and give that a compile. And hopefully we will now be able to bounce the ball off of the paddle. A key part in this game. Make that a little bit bigger. When I hit it with the left side of the paddle, it will bounce to the left, even if it's coming in from the left. If I want it to get to the right, just have to hit it with the right side of the paddle, hit it in the middle of the paddle to have it go up kind of straight. Excellent. Next, we should probably have the ball bounce off of the bricks as well and destroy the bricks. Maybe we'll do some kind of a scoring mechanism as well. Okay. So let's see, back to the level screen class. So at this point, we've checked if the ball overlaps any of the walls. We also want to check to see if the ball overlaps any of the bricks. So I think in order to make the code a little bit more condensed, I'm going to move this all into one big for loop where we iterate over all the balls. So I'm going to rearrange this code a little bit. I'm going to take this for loop where we're checking for collisions with the walls. And so check for a collision against all the walls. So this is going to handle ball and any object collision. If it overlaps with a wall, then we do this code. All right, now I need to remove these now useless for loops. All right, so we're checking for ball object collisions in this for loop. First, ball wall collisions. And if the ball overlaps a wall, we'll bounce against. This is ball paddle collisions. Right, we just wrote that code. And then ball brick collisions are very similar to ball wall collisions. Right, not only is it going to bounce against, we will also remove the brick. So I'm actually going to copy this code for ball wall collisions. Copy and paste and say ball brick collisions. And so for each base actor called brick, something derived from the brick class, if a ball overlaps a brick, and we prevent any actual overlap, and then we're going to bounce against the surface, but let's also remove the brick. Brick dot remove. Excellent. That is, after all, the whole point of Breakout is to break away those bricks. Okay, everything compiles. Let's go ahead and give this a run. Press space to start. Whoa, that was fast. I'm gonna have to handle reserve balls pretty quick. All right, let me try bouncing it up here. Now I bounce it off into the side. I am not doing very well at my own game. One more try. See if I can get this bouncing off to the side. There we go. All right, that appears to be working. Now we have to handle the case when the ball falls off the screen. It'd be good to give the player another chance, so to have some extra balls in reserve. Right, so for now, we'll say if a ball goes off screen and if there are no balls left on the screen, we'll perhaps spawn a new ball, and we'll make that message, press space to start that ball going again. We'll have that message become visible once more. So in the level screen class, let's do a few things. So if a ball falls off the screen, then we want to destroy that ball. If there are no balls on screen, but we have some balls left in reserve, which we'll add a variable in for later, then we'll want to spawn a new ball. Okay, first, how do we detect if something goes off the screen? Do we have a method to that extent? Right, we have an is on stage. I kind of want is on screen. We have a wrap to screen. Now, this is an important method, so let's actually add it to the base actor class. I could see many actor objects being able to use this. So let's say public Boolean is on screen. And the values we'll need here, we'll need a double for the screen width and a double for the screen, not a double screen, a double for the screen height. Okay, so what I need to do to check if it's on the screen, or would this be easier to write is off screen? It's off screen if, there's kind of 4 cases we need to worry about for off screen. So we're going to return true if any of the following statements are valid. Right, so for example, it could go off of the left-hand side of the screen. So if this dot get x plus this dot get width is less than 0, right, that means that the right edge of the object has gone past the left edge of the screen. So in that case, it would be off screen. Or, it's going to be a few cases here. This actor has gone off screen if this get x, the left edge, is greater than the width of the screen. Let's see, it has gone off the bottom edge. If this dot get y plus this dot get height is less than 0, it has gone past the top edge of the screen. If this dot get y, right, so the bottom edge is the y coordinate. Remember, in libgdx, positions are actually measured from the bottom left corner of an object. If this dot get y is greater than the screen height. If any of those are true, then the object is off screen. Right, so we'll go ahead and compile that. Oh, it's taken a while to compile. Okay, I think everything's fine now. We'll compile all the classes. And excellent. So base actor now has this method is off screen. Great. Now we'd like to use that method on each ball. Right? If a ball goes off screen, then it should remove itself from its stage. And so we can actually do that within the ball class, its act method. Let's say if this dot is off screen, this dot remove. Let's see. Oh, and I also have to tell it, of course, the size of the screen. This screen is 800 by 600 pixels. Excellent. So now the balls effectively self-destruct when they go off screen. Now let's head back to the level screen class. All right, so when ball goes off screen, let's spawn a new ball. Let's say if, let's count how many balls there are. If base actor, get list, everything on the main stage, derived from the ball class. Now I want to get the size of that list. And if the size of that list is 0, let's just go ahead and spawn a new ball. 0, 0 on the main stage. And since this ball, when we spawn a new ball, its velocity is 0, right? Its speed is 0. An earlier line of code in the update function will take over, and it should attach the ball to the paddle. Right? When a ball is spawned, its speed is 0, so the ball will move right above the paddle. Let's also make that start message appear again as well. Let's say start message dot set visible to true, so the player knows it's time to press start again. Okay, compiling all the classes. Let's run the launcher one more time. Okay, I'll bounce up, and the ball is back. It's good because I lost that game pretty quick. It's also kind of interesting. If I position it just right, I seem to be able to take out multiple bricks at once. If I can line this up so it's going to overlap more than one brick, I might seem to be better at this game than I truly am. But there we have it. We've got some nice breakout functionality. Right, we can now actually break the bricks. There's some other things I wanted to do. I really still do want to create a score. Hey, that's great. I want to create a score and an actual reserve ball counter to only spawn additional balls if we have any left. But we've done a lot in this video already, so maybe we'll take a break and we'll start adding a score and text elements and work on the user interface a little bit next time. All right, thanks for watching. one more. One more. Oh, here we go.